Welcome to example number 9. We have a ideal spring, I assume, that it has a force applied of 2 newtons to it and causes it to stretch 3 centimeters. Now if we slowly increase the force so that we get an additional 3 centimeters, we're asked what would be the new force that would be acting on the spring once it's now stretched to a total distance of 6 centimeters, and then determine the total amount of work being done from 3 centimeters to 6 centimeters. So first thing I would do is probably try to visualize this problem. So let's say we have a spring maybe attached to a ceiling, and right here at this position we'll say this is when the spring is at equilibrium. Then I attach a 2 Newton mass on this. And so when we put a force of 2 newtons, say a 2 Newton mass on this spring, now it's stretched 3 centimeters away from its equilibrium position. So now what we'd like to do is stretch it an additional 3 centimeters. So now when it's stretched this additional 3 centimeters, now the total stretch distance from the equilibrium will be 6 centimeters. And we're asked to find out in part A what would be that required force to stretch it to that length. There's a variety of ways of solving this. We could take, say, a graphical approach and look at it through Hooke's law. Let's construct a force versus displacement graph for this scenario. And hopefully you remember that from Hooke's law, the force is directly proportional to the displacement, so that if you were to, say, double the displacement, then you must have doubled the force. So you could simply just go, since F is directly proportional to x, and since the displacement doubles, then the force doubles. And therefore, the new force, force 2, would be simply just 4 newtons. You could write an equation for this graph here, for example, and write F equals, say, kx, and figure out the spring constant. So here's another way. You could use F equals kx. Let's find the spring constant for the first force at that displacement. We'll use 2 newtons, and then k, and then x would be 0.03 meters. And that gives you an approximate value for the spring constant of 67 newtons per meter. And then once you know that spring constant, you could find the force at the new stretch distance. So using 67 newtons per meter multiplied by the displacement of 0.06 meters, you'll get an answer that should be close to 4 newtons. Okay, well, let's go on to part B now. To find the amount of work done in stretching the spring, you could take a graphical approach. Since we've got a graph here, you could find the work done by finding the area under the force versus displacement graph, which would be 1/2 times the base times height, or really, I guess, actually would be finding the area that is from the initial position to the final position. Let me shade in that area here. We're really finding the area of this trapezoid, so maybe you can label this as base 1, and this is base 2, and this is your height. And so it would be 1/2, if you recall your formula for a trapezoid height, then times base 1 plus base 2. So this would be 1/2 times the height of that, which would be 0.03 meters, multiplied by base 1, which is 2 newtons, plus now what this base 2 would be 4 newtons. And this gives you an area of 0.09 newton meters or joules. Or you could take other approaches. You could find the area of this whole triangle, for example, minus the area of that triangle. And really what that is essentially doing is you're doing the work done equals the change in spring potential energy. So that would be 1/2 kx final squared, which is x sub 2 squared, minus 1/2 kx initial squared, which is x sub 1. And so you could use that approach, or you could take a common denominator of 1/2 k out, and then write x sub 2 squared minus x sub 1 squared. And substituting in your spring constant in your 2 initial and final positions, you'll get an answer that should be around 0.09 joules. So there's lots of ways of doing this again. Okay, and that's it for example number 9.